Hello? Okay. All right. Are we good? Okay. Hey, everybody. Can I have your attention, please? Okay, a few announcements before we begin. For the lab checkoffs, we're going to do the checkoffs again. Last week's lab is due at the end of this lab, so at 3:30. So if you haven't done that, you'll have a chance to do that after I stop speaking. And then, of course, today's lab will be due next week. And only one checkoff per team. So I mentioned last week, minimum of 2 to 3 people. How well has that been working? I know there have been a few issues with people losing their partners. The whole point of this is to get you guys to kind of like mingle and exchange ideas and learn from each other. Because, again, the docs are scattered all over the web, and so maybe one person can find something that the other person hadn't thought about. So is everybody okay? Does anyone have a strong preference for individual assignments? Awesome, cool. Is anybody in the class and not enrolled and wants to be enrolled? Okay, 1, 2. Okay, see me at the end or post on Piazza. And we'll just give you a permission number at this point. Yes?
Can you turn on email notifications, email receipts for the forms?
For the forms. Yes. The assignment forms? Yes, we can do that. Yes?
Did you say everyone on the team has to submit?
No, one per team. So that we don't have to look through different permutations of the same team members. If that's okay. Okay. So with that, somebody shut the doors on either ends. Thank you. Yeah, okay, so with that, we were talking about transactions last time. So we're not on the lab yet. I just wanted to finish off because I think this is important. So Bitcoin transactions. Tomorrow you're going to learn about Ethereum transactions and how the account-based model on Ethereum is different to the UTXO-based model Bitcoin uses. And if you recall, we talked about the UTXO-based model being unspent transactions, right? So we've gone through this, and these slides will be up online. So you saw this example. It was kind of complex. We talked about 3 different fundamental ways to carry out a transaction, where you can split. So you have to spend the entirety of an output. So you have these outputs pointing to you, and you have to spend their entirety. But if you don't want to spend like 100 Bitcoin, right? You only want to spend 1 Bitcoin. You can spend the entire thing, but direct 1 to where you want it to go, and then 99 back to you. So that was the basic idea. Additionally, you can group up various outputs that point to your address into one output that points back to you. So this would be the same thing as having like 20 quarters and then putting them all together into like bills, dollar bills, right? And then, of course, you have one big output, and you can split that up into multiple recipients. And that would be akin to things like payroll. I'm a manager, and I want to pay my employees. This is how I would do it. And all these examples are pulled from a book called Mastering Bitcoin that I brought last time, but I forgot to bring today. It's an excellent book. It goes very in depth into the mechanisms that Bitcoin uses. And it's great for people of all experience levels. So highly recommend it. Okay. And I think I mentioned last week that transactions were a lot more complicated than, in terms of data structure, than what we've described. We'll get into it in the protocol portion of the class. Is anyone familiar with the JSON format? Okay, so you can think of this as like a nested JSON type, and the important things are pointed out. But what I want to point your attention to is these things, right? So you have the script sig, and you have this script pub key, and well, basically this is the output script. So this is the input, and this is the output, all right? And looking at the output a little bit, there are two outputs, right? Here and here. And they're pretty much identical with the exception of this green portion. So that green portion is a pub key hash. And that is basically the person who is creating the output. That's them specifying the target, the recipient of that transaction. Is that clear so far? So the green is the target, who I'm sending the funds to. Now what is all this other stuff? Op dupe, op hash 160, op equal verify, and op check sig. Does anybody know? Or does anybody want to venture a guess? It's instructions, basically. Opcodes, right? And what it means is that outputs are actually scripts. They're actually mini programs that the recipient needs to then satisfy in order to spend that output. So let's see an example of how this would work. So this is our example. You've got, this is what we saw on the previous page, where you got op dupe, op hash 160, and then the pub key hash, and then op equal verify, and check sig. So you are assuming that this script, the bottom one, points to your address, and you want to spend that, right? So you need to provide a complementary script, and that's the top one over there. That's what you provide. You provide your pub key and your signature. Okay, and it's stack based, right? And so we're going to read the script in its entirety, and we're going to place it on the stack. So just to get you to like see what it looks like, okay, we're going to build it up. So this is the stack, and a stack is a first in, last out data structure. Does anybody know what that means? Or does anybody not know what that means? Okay, cool. So we're going to be placing things on the stack, and we can't remove the bottom one until the top one has been removed. So we're going to follow through. We place our signature, and now remember again, the top script is me as the spender. I am facing this encumbrance, right? So if I'm a customer at a coffee shop, I provide the coffee shop owner with my output, so I pay the coffee shop owner. It's the coffee shop owner's responsibility to run this script and fulfill its conditions. And this is the most basic kind of script. It's called a pay to pub key hash, P2 PKH. There are more complex scripts we can get into later. But this is the most basic and most common script, pay to pub key hash. So you're going to follow through. You're going to provide your signature and your public key as the coffee shop owner who wants to spend the money that you've been paid. So you put both of them on top of one another, and then you run op dupe. So op dupe is, you can think of it as a method or a function, but it's really an opcode, a Bitcoin opcode, right? And it duplicates whatever's on the top of the stack. So now you have two versions of the pub key, right? And then you say op hash 160. So you turn whatever's on the top of the stack to a pub key hash. And then you place the hash that the spender provided to you. You're claiming that this hash points to you, right? And the script is then going to verify that by running op equal verify. And so if the top hash matches the next top hash, so basically if these two hashes match, they're both popped. If they don't match, which means that you're claiming that the hash of the key that the person is pointing to is not the key that you have, the hash of the key that you have, then the transaction stops. You can't continue execution, and you can't spend that output. Okay, but think about this. Public keys are public keys, right? So I can see that there's an unspent transaction pointing to a certain public key. I can go and take that public key, and put it on the stack, right? I could just claim to be somebody else because it's a public key. So then how is it verified that this public key is actually my public key? Well, that's what the signature is for. And remember, the signature from last time is derived from my private key. So the only way for me to be able to sign this and have it match the public key is for me to actually own the private key. So, following that, it's verified that yes, it's pointing to the correct public key. But then we need to verify that also the public key that I claim to own is actually my own public key. I own the private key that matches that private key. And once that returns true, I can then spend that transaction. Somewhat complex, right? Is anybody confused? Right. That's fine.
It's the signature of the sender or the receiver?
This is the signature that the receiver placed at the beginning, right? So the first box up there is me as the coffee shop owner. I put down my signature, and then on top of that, I put down my public key. And remember that it was because we placed it first, it was last in the stack. It was at the bottom of the stack. So you would get to it last.
How do you verify that the sender has the funds?
That the sender had the funds. That's on the client side. So the clients, in order to verify, so your client is viewing the blockchain at the moment, right? And this is on the semantic level, which we're not going to cover. We didn't cover last week, and we're not going to cover today. But basically, the verification happens on the confirmation of blocks, right? And so if you put up a block, you're saying that, yes, I've checked this transaction, and this transaction is valid. And so every subsequent event that occurs after that, so say I'm the coffee shop owner, I can assume that the miners have done a good job of verifying that transaction. Now I see that there's an unspent transaction that points to my address, and I can spend that. So it's kind of unrelated, unless the coffee shop owner is himself a miner. Most people are not miners, and you can assume that safely. Most people who use the network are encumbered by the barrier to entry of buying an ASIC machine.
This is for basically like you say like the coffee shop side, So what was the whole point? Is this like the verification process for them to receive their money someone?
Yes, and actually it's not limited to just coffee shop owners.
It's not.
Yeah, no, everybody who transacts on the Bitcoin network has to go through this. Has to provide a complementary script in order to spend their transactions. Because outputs are not just like, my balance went up, my balance went down. They're all scripts. And hopefully, again, in the protocol segment, we'll teach you Bitcoin's native language, which is Bitcoin script, and you'll be able to follow through and create your own.
So the operation that you described a minute ago, that happens only when you want to actually spend your Bitcoin.
Yes.
And it just will sit it just sits on the blockchain until you go.
Exactly. So furthermore, like a more complex example of that would be a multi-signature wallet, where the recipient needs to provide multiple signatures from different parties in order to spend a transaction. And that's how, really, if you want the maximum security, or you want better security than just a pay-to-pub key hash, you would carry out transactions in that way, where you need multi-signature wallets. So like if you're on an exchange, the exchange, in order for someone to access your funds, you shouldn't only be able to access your funds with your own private key, because what if your private key is brute forced? So the way exchanges work is that they build multi-signature wallets that require your private key and also their private key in order for someone to spend your money. So that if you access your funds through their client, that's all done in the background. But if somebody tries to access your account through the Ethereum network, independently of, say, Coinbase or whatever, they won't be able to spend that through the Bitcoin network. Sorry, Ethereum works on the account model. They won't be able to spend that money, if that makes sense. Okay. So lastly, we get to the application layer. If you remember this diagram from last week, the application layer is a little bit nascent on Bitcoin. There have been applications built on top of Bitcoin, but they're way more obvious on Ethereum, where you can build using smart contracts. They're a lot more user-friendly, and we'll talk more about smart contracts tomorrow. Today, we're going to be working with Solidity, which is a smart contract language. So this is today's lab. Should say lab 1. I just realized, because last week's was lab 0. Anyway. Now, why is it a smart contract language? Does anybody know of any other smart contract languages? Viper, right. So Viper is a prototype language that's being experimented with right now. I'm actually working on the documentation for that at the moment, along with a few other people at Blockchain Berkeley. So how can we have multiple languages for the same thing? Well, the Ethereum network, it runs on an EVM, the Ethereum virtual machine, which is the first thing we're going to talk about, followed by the actual language and a couple of data structures, and then finally an exercise. And what the Ethereum virtual machine is it's a VM that runs on everybody's computer on the network. And once you receive a transaction on your node, you run that transaction on your VM, on your local copy of the VM, right? And what should happen, in theory, because the EVM runs deterministically, is that if everybody runs the same transactions, they should arrive at the same state. So if I broadcast a calculation that I'm doing, that calculation is 1 + 1 = 2, I'm not going to send the result to my peers. I'm going to send the transaction, 1 + 1. And if everybody runs it on the EVM, and because the EVM works the same way on everybody's machine, they should all arrive at the answer 2. That's an oversimplified example, but I hope it got the picture across. So that's what the EVM is. When you download Ethereum and you want to interact on the network, this is what happens. Now, the EVM reads bytecode. And the bytecode is composed of these granular opcodes: stop, add, multiply, subtract, and there's a lot more you can check out here. It's a lot more complicated than it first seems if you read the yellow paper. So I recommend starting with the white paper that kind of explains at a high level the philosophy behind Ethereum and why it was created and how it works and operates. But if you read the yellow paper, it goes into a lot more technical detail on that. And specifically, the Ethereum bytecode language is Turing complete. So there are loops in it, unlike Bitcoin script, which does not have jumps and loops. It's not Turing complete. And a lot of people actually dislike the idea of Turing completeness. Does anybody know why? So the reasoning is because it allows for malicious actors to maybe take advantage of certain security flaws that may arise in Turing-complete languages. Basically, a simplified version again is that with more freedom that Turing-complete languages provide, come more vulnerabilities and more ways to take advantage of ill thought out language features. Whereas Turing incomplete languages are more limited in what they can do. And so that's the philosophy behind that. More freedom equals more danger, which is traditionally not thought of as like, oh, you know, I want to have the flexibility. I want to be able to do all this cool stuff. But especially when you're dealing on decentralized network, security does come in handy because you're working with a lot of trustless parties, and also you're working with a lot of value. Right? I haven't checked the price of Ether today, but I would hate to lose even a single one. So, yeah, so we talked about its Turing completeness. It's also considered the world computer, or it's dubbed the world computer. It's this artifact of decentralized systems. But in fact, the way most decentralized systems are thought about right now is that you run things in parallel for efficiency, to run them faster, to get through them faster. For anyone who's taken 61C, you've gotten your first taste of parallelism and concurrent programming. But in fact, the Ethereum virtual machine, the way it works is that multiple systems, are not carrying out different processes in parallel. They're actually redundantly carrying out the same processes in parallel to arrive at the same state as each other. And so that's massively inefficient and a massive waste of computing resources. Waste here is subjective, depending on whether you think it's useful or not. But anyway, does anybody have any thoughts on that? Is anybody confused? What did?
I don't understand why you said that we only broadcast the transaction like one by one by example. Why not just tell everyone the answer so that we don't have to wait?
Yeah, well, so I would say read the white paper. That provides a much more succinct picture of why they do that. Anybody else? Okay. So, a quick overview of the language. This is what it looks like. Is it reminiscent of any languages that any of you know? So this is the code right here. JavaScript, right? Yeah, and that's what it was built to mimic. It's not JavaScript, but it looks like JavaScript. That's like the easiest way I can explain it. So this mimics a bank's function. And what does a bank need to do? It needs to allow deposits, allow withdrawals, and balance checks. And so we're going to go through it line by line and hopefully maybe decipher what exactly this code is doing. Okay, so we start off by instantiating, I would call it an object, maybe? Here it's called a contract. So this is actually what you would do to start up a smart contract. For those of you who have heard the term, this is what a smart contract would look like. For those of you who haven't heard the term, we'll deal with it tomorrow. Don't worry. Okay, so you open up a smart contract. We're calling it simple bank here. And remember, we're going to try to get this contract to mimic the functionality of a bank in three ways: deposits, withdrawals, and balancing checks. Right? Okay. We have then a mapping. So we are free to declare state variables, right, outside of functions. We have not seen any function definition so far. The first line after the contract definition is a mapping, which is basically a dictionary. If you're familiar from Python, it takes in a key-value pair. And here, we're specifying the typing. So the type that will act as the key will be addresses. And the values will act as unsigned integers, uint. And it's going to be private. And it's going to be called balances. So word for word, that's what all this means. Any confusion on anything so far? Yes?
Private in that sense.
So private in the sense that any external calls to that mapping will fail. So if you're trying to call it as a user, a smart contract has been deployed on the network, you're not allowed to do that. Of course, nothing's really private, right? What do I mean by that?
These are all publicly running contracts.
Yeah, these are all publicly running. And so if you remember last week, we ran the Rinkeby testnet, right? And what did you have to do to actually access the Rinkeby testnet? You had to download the blocks, right? Does anybody remember doing that or not remember doing that? You're very worried. So you had to literally download the data on the blockchain. And if we're saying that the smart contract is housed on the blockchain, right, and you have to run it on your local machine, we're saying that somewhere in the address space of this VM, right, we can find the source code of this smart contract. Kind of wild, I know, hold your amazement. But we can actually go through and try and find the bytecode of this smart contract on our local machines. Is there anything that's not clear? Awesome. Okay, so nothing's really private, but you have to kind of like work for it to see it. So when you say private, private is in terms of accessibility from an external viewpoint. You can still see it. You can see what's stored in it. Nothing is ever truly like hidden. But you cannot execute things that are private.
Any info about the overflow attack?
We'll get to that in our security lecture. So the address keyword? So the address is a data type. Like you have ints, you have strings, you have addresses. Yes? Yeah, so actually that's a great analogy. The comment there is contract like a class in Python? Yes. You can think of it as a class. And you actually do have things like inheritance, where contracts can inherit from parent contracts, certain methods and whatnot. Okay, so moving on. Last line here is you're declaring a public state variable called owner, and you're saying that owner is of data type address. So owner is an address. What does this mean? Okay, so I want to build an image of intuitively what we're doing here. We're defining a contract that's a bank that has a mapping of balances. So what we're saying is this contract is going to store a list of addresses and their balances. Keep in mind that it maps addresses to uints. So addresses are are representations of accounts, right, on the bank. And the uints are the balances of those respective addresses. Very intuitive so far, I think. And please let me know if it's not.
Could you explain like the syntax of the middle line?
Mapping?
Yeah.
Yeah.
So it's defining a function that is input and address is back out.
So it's not a function, it's a data structure. So the data structure is called mapping, and it maps addresses to unsigned integers. So if you imagine a Python dictionary, all the keys of a Python dictionary will be address types, and then all the values will be numbers, basically, unsigned integers. And it's private, and it's called balances. That's how you refer to it. Why is it essential that it's an unsigned integer? Why is that important? Someone put your hand up. Yeah.
You can't have a negative address?
Yeah. You can't have negative balance.
Oh, balance.
Yeah. So that's right. Unsigned integers cannot be negative. And that makes sense for this, right? Because there's no such thing as having like a negative amount of money. Simple bank, guys. Simple bank. Okay. Awesome. I'm glad we're getting there. Okay, so we have this other thing called event. And sorry for the sizing. I wanted to zoom in on certain things and didn't really pan out. But anyway, events. So these smart contracts are running on the network, okay, how do you find out what's going on? How do you run your tests, right? Well, you can run tests as listeners for certain things that happen. Instead of checking for state changes after something happens, you can listen for this event, log deposit made. And if this event is fired, then you know that the deposit has been made. Right? So basically, this is an event definition. We're defining the event. We're not running it so far. So this is another state variable. So far, we have not seen any functions. So let me go back. And I think, actually, Luke, have you gotten the PDF up on Piazza?
PDF is up,
Yeah. So if you guys want to have this pulled up, just to refer back to it, it's on Piazza. And so we're going through literally line by line and breaking things down. And so if you look at the top 4 lines, there have been no functions so far. We're just declaring state variables, state methods, state events. All right, cool. So an event is just something that fires, and you can actually see the event right here being fired. And it's literally a one-liner. It has no body. It's a method with no body. It just takes in parameters and basically prints those parameters to the network, so you can listen for them. You might go through this class and never use an event, and that would be fine. Yes?
So an event is a broadcasting mechanism?
It's a broadcasting mechanism, yes. Okay, so that's what an event is, and now we get to our first function, and it's called simple bank. Does anybody know what this is? It says it right there. Yeah, it's a constructor, right? So, what is a constructor? There can only be one method that has the same name as the contract name. And that's the constructor, and it runs on deployment. So you deploy the smart contract, anything that's in the constructor will run once and then never again. You cannot call it after that, and you can't stop it from running if you've defined it. And so what it does is it defines the local variable, the state variable, owner, as message.sender. So, remember, we defined owner. We didn't actually set it to any value, right? We just declared it. Well, here we're setting it to message.sender, and message is actually a built-in accessible variable that provides a lot of information. It provides details about the message that has been sent. So you can think of message as the current transaction that's being executed, and message.sender is the sender of that transaction. So I'm sending a transaction that is deploying the smart contract on the network, and because this is the first deployment, the constructor is run, and it sets the sender to owner. And furthermore, if I do not have any other method that changes owner, then owner will never change. Right? So once the contract is deployed, and I deploy it, I will be the owner permanently until the end of time. Or until the Ethereum network fails. So, question? Like a const. There is, yeah. Yeah, you can set things to const. Okay. Furthermore, we have a method, deposit, which accesses our mapping, balances, and it accesses the message.senders. So it's a little bit cut off, but I hope it's clear. So it accesses it the same way a dictionary in Python is accessed. The person who's saying deposit can specify some value, and that's specified in message.value, right? And so message.sender, say I'm depositing something in this smart contract. Message.sender is my address, Message.value is the amount I'm sending to this method call of the smart contract. And so this method is going to take message. It's going to look for message.sender and imbalances. If it doesn't exist, it's set up as 0, and it's going to add message.value to it. So now on this smart contract, on the mapping on this smart contract, there's a number that corresponds to my address on the balances, and this number goes up by message.value. And then I return this. I log the event, and then I access that mapping and return to the user how much they currently have. So say I have 0. I start off with 0. I deposit 10. What gets returned to me? 10. I deposit 5 now. What gets returned to me? 15. Okay, awesome. Everything clear so far? So returns indicates the return value of that method. So it says it's going to be an unsigned integer.
We can use message.sender as owner also, because the owner is equal to message.sender in the constructor.
So message is different for every transaction that you send. So if I deploy the contract right now, message.sender is me, right? But if you make a call to deposit, message.sender is your address, because you created that message. But you can use the keyword message here as kind of an abstraction for whoever's calling that the current iteration, the current execution of that method. Awesome. Okay, now withdraw. So it's public, it returns an unsigned int. And now, this is our first case of if conditionals, right? And this is how they're structured. And so we say that if the person who has a balance on this contract has enough funds, has equal to or greater than the amount that they want to withdraw, because withdraw amount is actually a parameter in this method, then we're going to deduct from their balance. And then, what are we going to do? Can anybody explain this if condition to me? Exactly. So actually, we're going to say message.sender.send that amount. And that's actually a method call in the conditional. .send actually returns true or false, depending on whether the call succeeded or did not succeed. And so it can be inputted into the conditional, and then this, if it does fail, then the balance is restored on the smart contract. Yes? Yeah, that's an interesting question. We haven't talked about gas. I would hold off until tomorrow. We're just talking about the language for today and semantics and how to use it, syntax and whatnot. Okay, so interestingly enough, something I haven't mentioned is that when I send the contract money, right, my balance, the number on balances goes up. And that's just a change in bits somewhere, right? But where does my money go? Like the money that I've literally sent to the contract. Does that make sense? So right now, the contract is acting as a ledger, keeping track of how much everybody owns, right? But my ETH is not a uint, right? It's represented as a uint, maybe. But it's not literally a uint. So where did my money go?
It's the address of the smart contract.
Yeah, so the smart contract owns that money now. Right? So say person A deposits 10 ETH. Person B deposits 20 ETH. The smart contract now holds 30 ETH. But 10, it keeps track of the fact that 10 belongs to A and 20 belongs to B. Does that make sense? It's this ledger of like ownership, of how much everybody owns. And so how is this relevant to like the bigger picture, right? Say I'm doing an ICO. And now just to display how flimsy ICOs can be, this is the exact model that ICOs take. There's a mapping, which is represented as a ledger of people's addresses and how much they own. And these tokens are fabricated out of thin air, right? We begin with saying, okay, there are 1,000 tokens to start with, and of these 1,000, 10 belong to person X, 20 belong to person Y, 30 belong to person Z. And that's it. That's how you buy your tokens. You put money into the contract, your uint on the mapping, on this smart contract, goes up a little bit. That's it. That's an ICO. Does that make sense to everybody? That blew my mind when I first learned about how Solidity works. But
So with that, you do not need to like instantiate the balance for a particular user.
yeah, so it's instantiated as 0 by default. Yeah. There was a question earlier over here. So. Okay, awesome.
Why did the deposit function take the parameters to the default mode? So why can't the withdrawal not be also packaged like message.value has been?
Yeah, great question. So the question is, why does the deposit function not take in parameters, but the withdraw does? And that's an implementation detail. But the gist of it is, with withdraw, you want to be granular, and you want to specify. You may not want to withdraw the entire thing. But you could create a simple bank where if the user wants to withdraw, they have to withdraw everything. In which case, you wouldn't need a parameter to be entered. You wouldn't need an argument. They would just withdraw. When they call withdraw, they withdraw everything.
So for deposit, then are you free to like constructing a method which by default goes to your address, but then you supply the value elsewhere outside?
You supply the value elsewhere outside the contract. Yeah, so the way deposit works, and the reason it doesn't take in any arguments, is that when you're constructing the transaction, because remember, state changes to smart contracts are represented as transactions. And again, we'll get into it tomorrow. But you specify it outside of the method call, how much you're sending. Because if you specify it inside as a parameter, it's just a uint. Again, it doesn't, I always think of the quote, you have no power here, right? Like, the realm that these methods operate on are not network-wide, but contract-specific. If you want to operate on the network-wide realm, then you specify it outside as part of the transaction that you send.
So message.send and message.value aren't actually inherent to this particular contract. It's something you do with the Ethereum virtual machine.
Yeah, it's something you specify as a command when you send a transaction. Like you specify the method call you want, you specify the arguments into that method call, and then you specify like the value that you're sending. You don't actually need to specify your address because that's done automatically. But you do need to specify your value because otherwise how would the EVM know how much you want to send?
So even if we publish our source code, how do we know that something is like doing what we want it to do for money?
What do you mean by that? So you as the creator of the smart contract?
Like me as a user.
Yeah, so say we're best friends, right? You and I. And say you want to buy a house from me. You could trust me, and you don't know how to program Solidity. You could trust me, and we could do an escrow-esque thing where we drop a smart contract, and you trust that everything is fair and correct on the smart contract, and you don't check it. I tell you what it does. Two things could happen. I could not be lying, and it works perfectly, or I could be screwing you over, right? So it's up to the user, in instances like this, to make sure that the source code works as described. Because of the nature of decentralized programs.
And how do you go about doing that?
Just read contract.
Could they like lie and publish like a fake like different source code? Because once it gets compiled, it's all off code, right?
Yeah, so you can, I'm not sure what the progress of this is, but if you're proficient enough, you can look at the bytecode and try and decipher it through that. I don't recommend it. The other way to do it is there are decompilers, I would say, that like reverse engineer like the bytecode to Solidity so that you can read it. And I would actually Google that. I'm not too sure if that works. Yeah. Wait until the security lecture, I would say. Sorry. We can talk about it afterwards, though. Yeah. How much time are we on? Oh, shoot. Okay. So, yeah. So there are a few more nuances here. Function balance is you can check your balance. This is a constant method. It doesn't change the state of the smart contract, and it returns a uint, and it just returns your access, right? So you access your address, and you can just check your balance, right? And so that's how people know how much is in the smart contract. Of course, again, you could go into the bytecode, right, and look at how much you own. But this is just a nicer way of doing that. And then, of course, this last thing over here, what is this method called? Right, yeah. So it's called nothing, all right? It has no name. It's a fallback function. Why do we need fallback functions? Someone calls a function that doesn't exist on the contract, just throws. In this case, it's not really, it doesn't do much. But say somebody sends money, right, into the smart contract, specifying a method that doesn't exist. Well, you need to have some mechanism over here to send that money back, right? Or else that money gets stuck in the contract, and actually the ownership numbers aren't assigned to anyone, so it's gone. It's just stuck there forever, right? If everybody pulls out what they own according to balances, you'll still have some like remaining balance in there that nobody can access, unless you put in a backdoor as the owner that says, okay, I can pull out this value. So everything following this is just documentation, some useful notes and whatnot. Oh, also, check in, please. I'll come back to this slide. But it goes over data types and data structures. So I'd say read through it, and then feel free to start on this exercise. So you have 4 things to do. One of these things I will show you in a demo. But for now, just make sure to check it. So yeah, break. We're at the 1 hour mark. Sign in. And yeah. Any questions in the meantime? Yes?
On the lab 01 that got posted, yeah, it says the code is small world, and I already submitted the attendance with that code word. Do you want me to submit it again?
Yeah, just submit it. It's fine, whatever. It's not important. Any questions about anything we've covered today, either about UTXO transactions or the Ethereum stuff, Solidity? Yes?
So if there is any bug in the Solidity code, in the smart contract, and you have made actually a transaction earlier with the user and who verified it's fine, but later on you found that there is a bug, and then you want to deploy the new version of that code, and where you may change the contract without letting the previous user know. So then how does that happen? Because it's a violation of what earlier contract was, right?
So let me just get the scenario in my head. There's a contract with a bug, and you want to deploy a new contract. How do you let other users know?
Yeah, and I have already made a transaction with other user with the buggy code.
I see. So you have a peripheral smart contract. So the question is, if I discover a bug in a smart contract, how do I then do version control, right? How do I push new updates to my code if things on the blockchain are immutable, right? Because you can't go back and change the source code of a contract that you've already deployed, right? So what you do is you run a peripheral smart contract. That smart contract points to the address of the smart contract you want to operate on. So it points to your current buggy contract. You say, okay, I discovered a bug. I'm going to deploy a new smart contract and change the pointer to point to this new smart contract. And then if you want to update that, I'm going to change the pointer to point to the new smart contract. Another update. So it's kind of like GitHub, but on the blockchain, if that makes sense. And that way, if people are only interfacing with the peripheral smart contract, then it should be seamless. It's like an abstraction. Does that make sense?
Yeah.
Awesome. Awesome. And that's actually kind of what Truffle does, which is the framework that we're going to be working with next week. When we actually, so here we're going to be working in an online IDE for this exercise today, which I'm going to show you how to do. Next week, you guys are going to start off with a local simulation of a blockchain and work on that. Yes. Any other questions? Yes. Events are most useful for testing. For testing that things got fired at the right time, when they were meant to, or if something didn't get fired, you know something is wrong.
Wait, so when you deploy a smart contract, what is actually going on in that deployment?
Yeah, so what is going on the deployment of smart contracts? Well, what you're saying is, right now, I'm basically compiling all the source code of the smart contract, all the Solidity down into bytecode, and I'm adding it to the network. Now everybody has a copy of the smart contract on their local machine that they can run. So if in the future they get a transaction that points to that address, they can run that smart contract given the inputs that transaction specifies, if that makes sense. So everybody basically downloads the smart contract on their computers, right? And every future transaction that interacts with that smart contract, you'll be able to run that transaction because of that.
So those transactions will always have a pointer to that contract?
So contracts have their own addresses. And so the transactions will specify the address of the contract that's being run, along with the name of the method that's being run, along with the arguments, if any, that fit into that method. And hopefully, because it's deterministic, you'll execute the entire thing correctly. You'll extract the correct smart contract and input the correct method and arguments, and also arrive at the correct return value. Did that answer your question?
Yeah.
Awesome. Yes.
Clarify my understanding of what Max asked a question about the security vulnerabilities. What happens if some nefarious actor decides to run a similar, but not quite the same, contract and try to fool other people into accepting valid states? Is the defense against that just the same as what occurs in the Bitcoin protocol?
Yeah.
Or, you have a consensus everyone else running the same contract for that one, and then if one person's state differs from everyone else, they can just choose not accept it.
Yeah. So that's exactly it. Unless you can launch a 51% attack, again, where you take over 51% of the network hash power, in which case you define the truth, right? You can't change the way the VM executes things, but you can change the current state. You would have to change the VM source code in order to change the way it executes. But anyway, the main thing here is that it is very similar to Bitcoin's consensus mechanism because they both use proof of work. Now, minor difference between Bitcoin's and Ethereum's proof of work is that Bitcoin uses SHA-256, while Ethereum uses slightly different ETH hash function. And also, Bitcoin is a little bit more centralized, or people claim that it's a little bit more centralized, because you can have mining farms, right? You can build ASIC machines that specialize in mining Bitcoin, in solving these cryptographic puzzles. Whereas with Ethereum, you can't do that. And there's some very complex protocol level stuff that entails storing a lot of information in memory, and ASICs actually do not have a lot of memory to work with, simply because they're very specialized in doing a specific thing. So you can't really build ASICs to mine Ethereum, which makes it a greener playing field, which means that it's not really about buying the best machine or the most expensive machine anymore to mine Ether. Anyway, a bit of trivia there. Let's get to the demo. Okay, so this is Remix IDE. One of the few official online IDEs out there for Solidity. And you can just go ahead and create a new smart contract by clicking on that, give it a name, and then define it. We're going to start off by specifying the version of Solidity we're using. Yes? Sorry. Is that better? Yeah, that's, I think. Is that okay? Awesome. Okay. So, start off by specifying the version of Solidity that you're using. And you do that just by stating pragma Solidity, and then 0.4.18, yes. Sorry? This is using the link? Yeah. So if you go down to, remix.ethereum.org, you should be able to access the IDE. And so I typed up a quick smart contract before we all came in. And I'm defining a string called greeting. And of course, I have the constructor where as soon as example is deployed, the constructor runs, right? And it sets greeting to the parameter _greeting. So actually, constructors do have parameters. You can specify parameters for constructors. And so it sets greeting to whatever I specify. And then later on, I can call greet and have it return the greeting that I specified on deployment. Right, so the way that works is I can say, right, so let me just comment these out. Okay, so the way this IDE works is you can specify inputs. So it picks up on methods, actually, that you specify in the smart contract and puts them over here. So I can go ahead. This is the constructor method. So I can go and say, give me a greeting, somebody. What's up? I heard what's up, so what's up? Okay. What's up, world? Okay. Okay, so I can create it. Awesome. So here it is. It's been deployed, right? And then I can click, it's deployed at an address, right? This is the address of that smart contract. I had deployed it previously, so this is that. But we're working here now. And I can click greet, and you can see that in the console, it's returned a string, what's up world, without greeting. Really simple, really elegant. I really like this IDE. Hope you guys find it intuitive to use. It's improved a lot since last year. Since 1.5 years ago when I first started using it. It's awesome, actually. There's a few other stuff. Environment, account, gas limit. Don't worry about that for now. But those are useful parameters that you can specify. This is under the Run tab, by the way. One thing I want to cover before letting you folks go and do your own thing with the exercises is that things like this error on compile time. And we've already covered a few of these. But if you read the docs, that should illuminate a little bit more what you can specify and what you can't and what you can do. And if anybody has any questions, Piazza is always there. But basically, uint, you can see the errors on the left. Uint is erroring because it's a negative number, right? We talked about that. Why is int 8 erroring? What do I mean by int 8, by the way? 8 bits, right? So why is it erroring right there? Roham, I think you mentioned something earlier, right? It's the size, right? It's like it's an int overflow, right? You can't represent a number that big with only 8 bits. So yeah, it's signed. So if I change it to 127, it's fine. Of course, if I had a uint 8, that's fine. Okay, so I don't want to get into bit size right now. It's not too complex, but if you're confused about this, make a post on Piazza, and I'll be more than willing to explain it. What's going on?
Can you just show one more time how you actually ran that example?
Yeah. So this window right here adapts really to whatever you specify. So if I don't specify a parameter in my constructor, it won't let me input anything into this field, if that makes sense. So first of all, it needs to not error. So get rid of any errors you have. And then, so over here you can see that string underscore greeting exactly matches that parameter right there. And that will be the case if you define any old function. So if I say greet string hi, right? So it's a string called hi. And I say, maybe I need to refresh. But, yeah, I need to redeploy. So hi, create. So now string called hi is expressed right there. I can input this into that method. Yes. Okay, so constant means that the state of the contract will not change as a result of you running this method. Does that make sense? So basically, if I say greeting equals hi, it'll give me a warning. Function declared as view, which is the constant, but potentially modifies the state, right? And that's kind of a conflicting thing that I'm telling the smart contract to do. And I don't think it will change the state. It will prevent the state from being changed if I actually do run this. Oh, by the way, okay, yeah, that's fine. Any other questions? Awesome. There's a lot more to Solidity. One thing you folks should know is that Solidity is infamous. People hate it, right? But it is currently the best tool we have to interact with the EVM at a high level. If you want to program in bytecode, be my guest. But Solidity is the best tool we have right now. And you guys are going to complain, and you guys are going to be like, why is it like this? And, man, like, what is going on? Especially when we get to this, a method to concatenate two strings. This should be intuitive, but it's not. I encourage you to give these exercises a crack. I'm going to upload the Google form to submit very soon. I would just say put it on a GitHub repo and then link the repo. Yeah, and of course partner up before the class ends so that we can do this. Any other questions? We have 10 minutes. For anyone who hasn't submitted last week's lab, a reminder that deadline is today. Please do so. And yeah, I guess we're done.
What's going on?
Yeah. What's going on?
Yeah, so it's saying that error, different example pending and debug.
Yeah, there you go. That's the input. And then, so what did you click? What was the transaction?
I just put hi,
Create. Okay.
just
Yeah.
creating and create.
Yes. So you created it, and here it is. There are two instances of that contract.
Okay.
So you can click greet, and it returns to you hi.
So does it mean we created the transaction?
So these are the contracts that you've deployed. So you can like deploy like a million contracts. And so like these are all contracts. And if you make changes and then redeploy, those changes will show up in the new contract.
And each of them has its own address, right?
Yes, each of it has its own address, and if you change the greeting for each one, they'll all be different.
Got it.
Hey, you made it!
Yes.
Awesome,
yes,
awesome.
yeah.
Good to see you.
I wanted to ask you if you can. So I can be enrolled like officially. I can just audit courses. So can you admit like to?
Yeah, it's